I've decided to work through the molecular orbital diagram on the practice quiz, the mock quiz. So you were given a series of compounds, Li2, two lithium atoms, making a molecule, diberyllium, dilithium, diberyllium, lithium, beryllium plus one. Doesn't matter if these compounds actually physically exist when you make an MO diagram, or I should say if they've actually been discovered, but the MO diagram can give you some insight into, is it even possible that these compounds could exist? We'll see there's a way to apply MO theory to the solid state as well, in case you're wondering about how lithium could form a compound. The first thing to think about when you're doing an MO diagram, and it's not explicitly on the MO diagram, of course, the atomic electronic configuration, ground state electronic configuration of the atoms in question. So lithium, 1s2, 2s1, excuse me. Beryllium is 1s2, 2s2. Now in the MO diagram I gave you, we have a 2s orbital, another 2s orbital. They form a sigma bonding MO and a sigma star anti-bonding. There is actually the 1s bonding orbital. It would actually be lower energy here, but that orbital set would be full, so it's not going to contribute to the MO diagram. So that's why I've left it off, in case you were wondering. And I'll talk more about that in class. If this was looking at elements that are 3s, 4s, 5s, this would stay the same, just the quantum number would change, because regardless of what the n number is, you've got one s orbital. One of them would be coming from, if this is, two lithiums, there'd be a lithium here and a lithium there. So, without further ado, if I have two lithium atoms, I can start off like this. I can say I've got an electron here and an electron there for each of the lithium atoms. Where you have to keep track of your system is, when you put them into the MO diagram. So I've got a total of 2 electrons that are going into my MO diagram. Whether you erase them, cross them out, doesn't matter. So 2 electrons, they go to the lower energy bonding MO, and the sigma star is empty because we only have 2 electrons. Again, where I see this mistake happen many times is if you forget you just use these 2 electrons, then you look over and you say, I've got 2 electrons here and I've got 2 electrons there, so you put another 2 in there. But that's nonsense, because again, you can only have as many electrons as are brought in the system, assuming there's no charge. And in this case, it's lithium, 2 lithiums, but no charge. So this would have a bond order of 1.0. Remember, bond order is 1/2 of the bonding electrons minus the anti-bonding electrons. I've got the numbers and all that kind of stuff worked out, posted on D2L, but I want to go through this conceptually. Paramagnetic versus diamagnetic. That was the other question I was asking. Well, 2 electrons, and they're both paired, so that would be diamagnetic. Now you might make the argument of, why can't I do this? Why can't I just go boop, all right, and then do that? This would be an excited state. This would not be the ground state of our species. What would happen is you would have to put in some type of energy to take the electron from the bonding orbital and throw it up into the anti-bonding orbital. So, unless I were to ask for something explicitly like an excited state, that would not be viable. So bond order of 1.0, and it is diamagnetic. With a bond order of 1.0, in theory, a diatomic lithium molecule could exist. It'd have a single bond. But now we get to beryllium. So beryllium, 1s2, 2s2. So each beryllium atom brings two electrons to the party, if you will. So again, atomic orbitals, molecular orbitals. Again, it's very important to understand that distinction. We bring atoms together to make molecules. So we're going to have 4 electrons. I put in the first 2 in my bonding MO, as we did with lithium, diatomic lithium, but we have 4 electrons. So the next 2 must go to anti-bonding. 1/2 of 2 minus 2 is going to be 0. So the bond order of diatomic beryllium is 0. Paramagnetic and diamagnetic really doesn't matter because this molecule, by definition, cannot exist. Again, by inspection, we would say it's going to be diamagnetic. But if you think about it, that's kind of a moot point because the molecule can't exist. If you have a bond order of 0, there's no chemical bonding occurring between the 2 atoms. Now, where I change things up a little bit is now I've got a lithium with a beryllium. It doesn't matter which side I put them on. So if I put, let's say, I make that the lithium, well, lithium is 1s2, or 2s1. So there's its 1 electron. 2s2. So now I'm going to have 3 electrons. When you have an odd number of electrons, right there, that tells you the system is going to be paramagnetic. By definition, if it's an odd number of electrons, you can't pair everything. That doesn't mean even systems cannot be paramagnetic, and we'll see that with d orbital sets, but odd always will. So 3 electrons to work with. By the way, it does not matter the order that you put the electron spin in. This kind I'm putting it spin down, and then therefore the next one must go in spin up. They always have to be paired. So just to be different, I'll put the third one in, as spin down. Normally I draw it spin up. It doesn't matter. 3 electrons, 2 in bonding, 1 in anti-bonding. The bond order would be 1/2 of 2 minus 1, which would be 1/2, 0.5. So this, LIBE, that molecule in theory could exist. The chemical bond, because it's a half bond, would actually be weaker than diatomic lithium. It would be paramagnetic because, again, by inspection, I can see I've got 1 unpaired electron in the anti-bonding orbital. 3 electrons, they got to go somewhere. We'll look at more complicated MO diagrams later on, but right now, as we're looking at the S ones, it's pretty straightforward. We bring in 2 atomic orbitals, we make a bonding and an anti-bonding. So you always have to incorporate the orbitals that you start with into your MO. Even if they're non-bonding, we'll see, they'll end up in there, they just simply won't participate in the bonding. LIBE plus 1. So, actually, I shouldn't have erased that, but okay, so this was the MO diagram for LIBE, lithium with beryllium as a molecule. If it's LIBE plus 1, now I am removing 1 electron. All MO diagrams are with respect to energy. So we fill the bonding, which is at low energy first, then the anti-bonding. When we remove, we go in the opposite order. We take away from the highest energy. Okay? So this would be the cation. Well, now my bond order is going to be 1/2 of 2 minus 0, which is 1.0. So the chemical bond, LIBE, neutral, had a half bond. This, with the cation, will actually have a bond order of 1.0. That's actually a stronger chemical bond. So it can exist, it's going to have a bond order of 1.0, and it's going to be diamagnetic, because I removed that electron, the unpaired one, and these 2 are paired.